Okay, so we do have an exam tomorrow. What I would like to do today is I have, based on your homework, based on the homeworks that we graded, I have some review material for us for the exam. So what I would like to do, though, is finish up the material on the quick sort, because we started it last time, and then spend the last half of the lecture time talking about what's going to be on the exam, what the format's going to be, and then I have some review material that's I think will be helpful based on the homeworks. So there's some weaknesses there that we can review. All right, now, so we were right in the middle of analyzing the quick sort, and we had just written down the loop invariant, I believe. Is that what we did at the end of class last time? I think so. And so figure 4.17 shows a diagram of the three regions of the array during the execution of the loop, going from low to high. And what happens is there's the first region is the region where the value of all of each array element is less than or equal to key. The second region is the region where the value of each element in the array is greater than key, and then the third region is the unrestricted region. And what happens is J is a loop. J is the control variable of the loop, and it goes from low to high. And as it goes from low to high, what happens is the unrestricted region starts off to be the whole thing, and then as J gets closer and closer to the end, the unrestricted region shrinks and shrinks and shrinks until pretty soon the only two regions left are the regions where the elements are less than or equal to key, and the region where the elements are greater than key. And then, so let's go through a little exercise here to see how to prove that the split method, the split algorithm, is correct. So here, what we have on the next slide is we've rewritten the loop invariant, okay? And the first thing we have to do is we have to prove that the invariant is true at the beginning of the loop. So how do we prove? Remember, there's four parts. You prove the invariant is true at the beginning of the loop. What's the second part of the proof?
It stays true.
It stays true each time you go through the loop. And the third part is to show that the loop terminates. And the fourth part is to say
the postcondition is
the
true.
postcondition is true. Yeah. So let's do, and a couple of these we can do formally. I think it'll be a nice little review of our discrete structures. So the invariant is true at the beginning of the loop. So what happens at the beginning of the loop? So we start with the invariant, so we just write down this invariant. And now, what was the code? What did the code do at the beginning? Do you remember what the code did? Let's go back. Here, up at the top there, what does the code do?
We have to assign the key and mid.
Yeah, key gets assigned and mid gets assigned to low. Is everybody clear? So see, you look at that, you inspect that code. So the assignment is that mid gets low. Oh, and also J gets low, right? Because it was for int J gets low, J. Are you with me? So what changes here in this loop invariant? What do we do now? The M, yeah, we replace M with what?
L.
L, and we replace what?
J with L.
J with L also. Does everybody see? So that's just a simple, we look at the assignment statement, and that's what it does. So now what do we have? We have, for all I, L less than or equal to I less than L.
False.
Yes, and how can L be less than or equal to I, but then I be less than L? The only way that can happen is if L is less than L, right? But L can't ever be less than L, so that's false. What about, oh, that's on both of them, right?
Yeah.
So by math, that's false. All right, you guys, a little review of discrete structures. What happens if we have false in the range? It's the what? It's the empty range rule. And with the empty range rule, what is the value of the quantification? It is the what of the? It's the identity of the operation. Now, what's the operation of for all? Is that conjunction or disjunction? That's conjunction. It's and. And what is the identity of and? True. see some happy faces here remembering this stuff. So the empty range rule says that that's true and true. And what do we know about true and true?
It's true.
It's true. So it's true. Now, so by item potency or the identity of conjunction, either way, it's true. Now, I noticed on the homework that some of you guys, when you write down a loop invariant has to be a Boolean expression. Some people wrote down a summation that added up to be a number. A summation by itself cannot be a precondition or a loop invariant, because but if you say S equals that, then that is Boolean. Do you see? So some people made you made some type errors on that. Does everybody see? But note that this is Boolean. This is a Boolean expression, okay? And then we have to show that the invariant is maintained with each execution of the loop. Now, I don't want to write all this stuff down, and there is an argument in the book, but let me just go through verbally and make that argument. Okay, so let's go back here to figure 4.17. So let's take a look at the if statement, and first let's see if the condition is false. If a sub j is greater than key, then all that stuff in the if statement doesn't happen, right? Yeah. So the only thing that happens is what? J goes up, j plus plus. So look, so here in the figure, if j goes up by 1, then what we are doing is we are including a sub j in the greater than key region, right? So it is. So therefore, that element is also greater than key. So therefore, all of them, including that one, is greater than key. On the other hand, if the if statement does execute, if a sub j is less than or equal to key, what goes up? Not only does j go up, but mid goes up, right? So what happens is if we swap a sub j with a sub mid, what are we doing? The item that was within a sub j now goes to mid, but then if after that mid goes up, then that element is in the what? Less than or equal to key region. You see? That element is in the less than or equal to key region, and if that, because mid will go up by 1 after that. But in fact, it will be, because that's the guard, that's the if. The if statement says if a sub j is less than or equal to key. So that one is in the right place. And furthermore, if we are, but now what's included in the new greater than key region when j goes up? It was the one that was at a sub mid, but that one was already greater than key. So that's how you reason that out. Okay. And then the other thing was, what was the next one? How does the, so C takes the loop terminates. So how can we argue that the loop terminates?
J increases.
Yeah, J starts off, yeah, it increases.
Low and goes to
Yeah, so it has to start off to be less than high. And so if you increase it by 1 and high never changes, eventually it will equal high. So eventually the loop will terminate. And now we can do the last one, the post condition holds at the end of the loop. And this one's pretty straightforward. Starting with the invariant, so there's the invariant again. And then what happens at the end of the loop? We just note that the j keeps going up and up and up until it's what?
Oh, yeah.
Yes, I think until, well, yes, it's 1 greater than high.
Yeah.
Right, so it's so what does j, good point. So the final value of j is h plus 1, so what do? We put h plus 1 in there. Okay, so wherever there's a j, we put an h plus 1. And that only happens what? On this one over here, right? Okay, but now what is I less than h plus 1 mathematically is equivalent to what? Less than or equal to h. So a little math, that's less than or equal to h. And now we actually, here is some, you know, you asked the other day, what about having all these other ones be less than all the other ones? Do you remember you asked me that question? You see, yeah, well, you were saying, well, wait, don't we have to show that every value in this, on the left region is less than or equal to every value on the right region. And my comment was, well, that's not what the loop's doing. It's comparing it with k. So all these ones are less than k. But now here's where we reason. Here's where we use the reason to show that the post condition is true, because the post condition is that all of these, every one of these is less than every one of these. So what we have to do is it's the transitivity of the less than operator and logic, because if all of these are less than the key, so if this is less than the key and the key is less than this, then this is less than, you see what I'm saying?
Yeah.
So you would have to make that argument. And so this is the second post condition of sort. So even though we're not using even though quick sort is not on the exam tomorrow, I think going over this is a good review, as a good reinforcement for how to do these proofs. And also, one of the things you know is going to be on the exam tomorrow is how to write down a recurrence. So even though this particular one might not be on there because this one's quicksort, this is going to be practice on writing a recurrence. So now, you guys, let's write down the recurrence for this. Okay? Now, here, I'm going to put something up here that I think will help us to see what the performance is. So let's write down those four. Let's write down split. Here's what we have to be able to reason through. First of all, we understand that there is a best case and a worst case for quicksort, because it's using a random number generator to do the split, and we don't know how good the split's going to be. We don't know how good the split's going to be. So what we're going to have is we're going to have to do two different scenarios. One where the split is exactly in half each time. That's the best situation. The worst situation is if by some really unlikely event, what would be the worst situation?
Just cuts off one each time.
Yeah, it splits way just one and then n minus 1. Are you with me? So here's what we're doing, you see? So here's my question first is, what is the best case recurrence? Now look here, you guys. In the best case recurrence, tell me, what is this one? How does the split, what's the big theta of the split? This is going to be best case now. What's the big split? What does the split have to do? And well, yeah, but is it a big theta of 1? Yes or no?
Big theta of n.
It's big theta of, the answer is no, it's big theta of n. Why? Because it has to go in a loop, right? Switching, right? So this one's big theta of n. Are you with me? Now, how about this one? How about sort A, low, mid, minus 1?
It's just 1.
No.
You say it's the same,
What?
or it's half of what the whole.
It's half of what the whole one was. So what would that be? What would the time be to do this?
N over 2.
What about close but no cigar? T.
Oh, yes.
If T is the time to do n, then T, not 1/2, but n over 2. It would take this T of n over 2. Are you with me?
Have you said probably before, but like, why sometimes you write T and sometimes you write theta originally?
Oh yeah, see, because that's a good question. Because you write the T when in the recursive call. You see, we are writing how long it takes to sort. T of n is how long it takes to sort n elements. If T of n is how long it takes to sort n elements, then T of n over 2 is how long it takes to sort n over 2 elements.
Okay.
Are you with me? Whereas this one could be 5, it could be 7, or 2, or 1, or, and so we don't know exactly what the constant is, but the main thing is it's big theta of 1, yeah.
So if sort was an iterative function, would you use theta instead of t?
No, you would, if it, but sort, yeah, but that's the,
So you use.
no, the reason we use T here is because it is recursive, and we are writing down the recurrence. We wouldn't write down a recurrence for an iterative one. We do statement execution counts.
Okay, so that's what.
Yeah.
You use T for recursive.
Yeah, yes.
Theta for non-recursive.
No. Theta even comes in here. We're doing this recursive thing.
Okay.
But split is not recursive.
Correct. Split is not a recursive call. It's a loop, and that's why this big theta of n.
Yeah.
Yeah, so that's why, so because split is not a recursive
Right.
function, you're not using T, but since
Right.
you're using T.
Yeah.
Okay.
Because the definition of T of n, what we're trying to write down is the recurrence for T of n, which is how long it takes to sort n elements. So now what would this one be? T of n over 2. And do you remember what the join was?
It's just one.
Isn't it 3n, so it's just n?
I don't think so.
It just happens.
Well, but you have to like go through all of the things.
No, the join. No, shoot, the join.
You don't need a.
You just calls join. It doesn't do anything. It returns.
Oh, yeah.
Right. So it's big theta of 1. Now, does everybody see how we reason this through? I think even though this is not going to be on this particular one might not be on the exam tomorrow, or isn't it? This way of doing recurrences is a good review, I think. Yes.
Isn't split called again though for every time that you like?
Well, it will recursively. That's all in here. It will recursively do the split. But all that's in here.
Okay.
You see?
So
because look, this corresponds to the code.
Oh, okay.
This corresponds to the code.
Okay. So split doesn't call any other function.
Correct. Remember, it was just the loop.
Yes. Okay.
Yeah.
Okay. Yes.
Yeah. These are all really good questions. I think we're starting to see how this all works. Yeah.
Oh, great. Our homework was not quicksort.
No.
Great. Okay.
No. All right. So now tell me, you guys. Now tell me what's the best case recurrence. Now with this, what's the best case recurrence? Well, what's always at the top? I mean, what's always the base case is what?
Theta.
Big theta of 1. But now what about the other one? What about if it's greater than
2t n over 2.
2t
Plus theta.
n over 2 plus what?
Theta of n.
Now, does everybody see how that works? Are we good?
What if there wasn't one of them that was big theta of 1?
If this were big theta of 1, it would be, see, big theta of n plus big theta of 1 is big theta of n. Think of it like this.
Okay.
Big theta of n plus big theta of 1 equals big theta of n. Because this represents a function that executes on order n times, and then if you just add a constant to that, both of them together, and you do this one after this one, both of them together is a function that executes, you see, n plus, this adds a constant to what this one would be.
What if there was another call in there, which was an n squared?
Yeah, then what do you think big theta, good question. What do you think big theta of n squared plus, and then you had another one that happened later that was big theta of n. In fact, we're going to come up with this.
Is it still just?
What do you think this is? What do you think this equals?
I think it's just n squared.
It's big theta of n squared because that's the one that predominates. It was like if this one executes. Yeah, good questions. Good questions.
You would never have like on that bottom part. You would never have big theta of something plus big theta of something.
Right. You would do this. You would do this reduction. Yeah. Now that's the best case. But now what's the worst case? Well, we're going to have to go through this and do the worst case. All right? So that's the best case. Now my question is, wait a minute. One more thing. Does that look familiar? Does this big theta of n plus 2t n over 2 plus big theta, does that look familiar? This is a review for the exam. That's the same as the what? Merge sort. So what is it? The solution is what? Big theta of n log n. What's the worst case recurrence? How do these change?
The first one doesn't.
Okay, so this one is what?
Still the same.
This is big theta of n. Now what will happen is, in the worst case, one of these, let's say that let's see, this is low to mid minus 1. So let's say that the split is way over here, you know. So to sort between so let's say that mid is way over here on the high end. Then how long would it take to do this one? How long would it take to do the leftmost one that has?
Like n minus 1.
Yes, this would be what of n minus 1? Theta or t?
T of n.
Oh, good. T of n minus 1. And this one would be what?
T of 1.
Yeah, well, t of 1, but one element is just boom, boom. So, I mean, we wouldn't need to say t of 1. We could just say theta of 1.
For recursive type.
I know, but it's only one element, so it doesn't repeatedly call. So we can say that this is big theta of 1. Do you see what we're saying?
Were we saying mid was like?
In fact, t of 1 is big
second to
theta
last
of 1.
element? Was mid the second to last element?
Yeah, maybe.
Yeah,
Yeah, well, the question is it mid equals high or is it mid equals high minus
I
1?
think it's high minus 1 and then the other.
Here, it's on figure 4.17. It would be this situation every time.
Mid is high.
So mid is high. It would be mid being high. Is everybody clear? Okay, so now here we are. So, and now what about this?
Still.
Big theta of 1. Now, does everybody see how we're doing this? And so now what's the recurrence? If in the base case it's what? Big theta of 1, but then in the other one it's what? Are we good?
Is that like how are we to say that that's like worse?
That's the worst case. And the worst case occurs in the quicksort if the unlikely event that it is split off just one element each time.
Well,
I mean, it might be an astronomical probability that ever happens. In fact, I can tell you that in practice, it never happens. In fact, you can show that in practice, on the average, I mean, if it's a truly random number generator, it will be the same as big theta of n log n. That is a result that is mathematically provable, but that we don't have time to do. It involves probability and probability distributions and stuff like that. Did that answer your question?
Well, I just mean like it's not necessarily apparent that 2t of n over 2 is better than 1t.
Oh, well, here will be the mathematical proof of that. What do you think is the solution to this recurrence? If you look in the back of the book, there's a, what do you think? If you look in the back of the book, there's an example with numbers here of t of n minus 1 plus big theta of n. Can you think of what this is?
The n squared.
That's exactly right.
Is that something we'll have to know how to do?
If I could give you a problem that says, if I gave you a problem that said, prove that this is a solution to this recurrence, and it happened to be that one, you should be able to do it.
But we don't have to come up with a solution. Like,
But let's think about it. Let's think about it.
Yeah.
Why do you suppose it's n squared? I mean, can we get our intuition up to speed here?
It's bigger than
Because what happens? Each time you do it, it's big theta of n minus. Yeah, say it again.
You have to do big theta of n something, n times.
Yes, you basically, each time you do the Tn minus 1, you're doing theta of n.
Okay.
You see? You're doing big theta of n, basically n times. Okay, so that's the end of the quicksort stuff. But I think this is good. I think this was a good review for the exam anyway, just because it shows us how to do recurrences again. Yeah.
Did merge sort have a best in this case?
Good question. The question is, did merge sort have a best case and a worst case? That's a really good question. Let's think about that. This stuff that's a good thing to know, that we all need to know. Did it? Yeah. Did it have a best case and a worst case? Yes or no? No. Why not? Because it guaranteed what?
It
was sort of
No,
split.
because it was guaranteed. How did we do split? What was the code for split in merge sort? This, by the way, you should know. If I ask you to re-implement the split in merge sort, you should be able to do that. You should be able to write the code for that. What is it?
Well,
That was a different question.
Oh, different. Well, I want to know how did
what was split?
what was this code for split?
Mid equals low plus high plus 1 divided by 2.
2, exactly. Mid gets low plus high plus 1 divided by 2.
there's no-
So every time, so every time it did it in what? In half. And then when we wrote down the recurrence, and we saw that it would be n log n.
Oh, and
So
then
that's a guarantee.
even if it wasn't like even on both sides, it was never like all the way.
Well, I mean, the only thing it could be off would be like by 1 if
Yeah,
there's an
yeah.
odd or even number of elements,
It wasn't the-
odd number of elements, but still. Yeah, good thing to know. All of this is all very basic stuff to know. Okay, now for the exam now, I think on this exam, this is our first one. What you should know is, first of all, how to do all of the homework exercises. Okay, so that's just a given. And then you should be able to know how to do the code for the code that you did for the exercises. So there will be, let me just state, there will be problems, and this is true throughout the rest of the course. I will ask you to code in C++. Okay? Now I'll give you the parameters and the attributes, if you need the attributes to use in the code. So I'll give you whatever you need. You don't have to memorize what the attributes are of a class. I would give that to you, but you do need to know how to code. And many years ago I thought, well, let's try to have people do it on the computer because you have a compiler, and trust me, even though you're writing it on paper, the nice thing about writing code on paper is that you don't have a compiler screaming at you that it doesn't compile. And you can just go on, and I can see your thought process by what you write down on the code on the paper. So, yeah, question?
Do we have to bring those little green books?
No, you don't have to bring the little green books, the exam books. So it'll be all I'll just leave a space on the page for you to write the code. Yeah.
Will it kind of be like the homework assignments where like it will be exercise left for like the reader, but instead of like that, it'll be
Yeah.
blank when you write it down.
Yeah,
So you
yes.
won't have to like write out like the framework of like implementation, like a template class.
Right. No. I won't. A lot of that template class stuff and the file I/O and all that stuff, that's just grubby details. We are interested in the algorithm itself. So let's think about the data structures that you did since the first day. We started with the shapes. That was pretty easy. That was pretty easy. I mean, that probably won't be on there just because that's so easy. I mean, that was just to get you up to speed, right?
We have a bonus question.
Then what did we do?
Array T.
We did array T and array P. But you didn't have to code array T and array P.
Oh, right. We should
And the key concept there was what?
segmentation.
Was going outside the bounds of the array. Yeah. And actually, that involved overloading the, do you remember that was like operator square bracket? Yeah, but even that, knowing how to do that operator overloading stuff, that's something that's not, I wouldn't ask that.
Does that even have a name?
What? Yeah, operator, it's overloading the subscript operator.
Oh, okay. I like that.
Okay. But but then after we did that, do you remember what we did? What the data structure was that we did?
Oh, vector.
Vectors. Vectors, definitely. And you might as well just do the P, the vector T is the one that you should know for that. And that you should know how all of those work.
Was that the one that when you insert something?
Yeah, when you insert, you have to shift over, blah, blah, blah.
What was the capacity? How were we supposed to implement that? Because it had to be like,
You did it. Oh, by the way,
how hard? I couldn't figure it out.
oh, well, but I gave you the, we always try to give you the solutions of the code that didn't work. We always try to, so, and by the way, you guys, we are going to use vector P and vector T in future data structures. So you might as well now, if you didn't get that one, you might as well go and pull those unit tests up and get that sucker to work, because we're going to be reusing it. Elements of reusable software in the DP4DS distribution.
Is it
Yeah.
possible for your unit tests to work, but you just still have something wrong?
You know, that is such a good question. The question is it possible for the unit test to work, but for something to be wrong? And actually, that is such a good question. I'm going to give you a famous quote by a very well-known computer scientist. I believe quote is by Dijkstra, who is no longer with us. He passed away, unfortunately, a few years ago. And the quote is this. I'm not even sure now if this was Dijkstra's quote. But anyway, it's a good one. And it is something that he would have said. He said, testing can only show the presence of bugs, never their absence. Now think about that. When you test something and it fails, you know there's a bug that's in there. If you test something and it passes, you can't be sure if the test just failed to exercise that combination of, that circumstance that caused it to fail. And that's why correctness proofs are so important. And it's really important when you get to concurrent algorithms. So the answer is, it is possible. I have tried to design the unit tests so that if it passed the unit tests, then it's good. But I will have to admit, I have had to go back and modify my unit tests when a student's code didn't work but it passed the unit tests, and then later on when we reused it, it turned out that the implementation was incorrect because my unit test didn't test that condition. Mm-hmm. So over the years, I've gone back and I've improved the unit test. So the answer is, I can't prove it. I mean, that's not a 100% guarantee. But they are, and you see why it's difficult. It's because there's so many possible corner cases. Yeah. But I've tried to make the unit tests be as robust as possible. These are all really good questions. That was a really good software engineering question. Yeah.
Do we need to know how to do proof of correctness for a loop?
I might ask you to do part of one. I think it'd be too long to do the whole thing. I might give you some code and say, prove that the loop invariant is true at the beginning, or prove that, argue that the loop terminates, or whatever. I mean, I think it'd be too long to do a whole thing. But definitely, and how to write down a loop invariant. Yeah. So the exercises include statement execution counts, proving big O, big theta, big omega, let me say that again. Big O, big omega, and then those together give you what? Big theta. And I have some review material and then obviously you have to be able to prove that a proposed solution is a solution to a given recurrence. You should be able to write down the recurrence of some code that calls itself recursively. Yeah.
Will there be material that we haven't seen yet? Like in terms of obviously material we have seen, but like an expanded version of it? That's
Obviously, I'm not going to give you the statement execution count that we did over in class, and I'm not going to give you the statement execution count that was your exercise. That'll be different. You have to know how to do that for different scenarios. So yeah, that's the way that's going to work.
Okay. Could you give us one that's slightly easier than the whole?
Well, actually, that's one of the things here. I've got some review material on that and on some other errors that I found in the homework. So you want to? Shall we do that? Okay. First thing let's do is there are the steps in proving big theta and the steps in proving big O or big omega. I want to review some of these. So look. Suppose you say 4n squared minus n, and you want this to be less than or equal to 4n squared minus n squared. How can you justify this? What do you, when is it, but the question is, what's the proviso? You see, in other words, when is this true? Is this true for all positive n or what?
Well,
Greater than 1 or greater than 0? That's the question.
but that's, no, it's not. It has to be less than 1.
Oh, sorry. Wait.
Yeah, it should be greater than.
Oh, this should be greater than or equal to, sorry.
Let's be greater than 1 then.
Yeah, great.
Yeah, it's 1, it's not 0, right? So this is increasing a negative magnitude, right? For n greater than or equal to 1. Because if n is a half, then you're multiplying it by a half, and it's not increasing. Okay, so that's 1. Here's another one. How about we say 2n squared? Man, my notes are all wrong on all of this stuff. Suppose we say 2n squared plus n log n. And we want this to be greater than or equal to, oh no, this is right, greater than or equal to 2n squared. In order for this to be greater than or equal to, in other words, just to drop this, in order for this to be greater than or equal to this, is this for all n or what? That's the question. This is the question. Is a proviso. Is this true for all n? Yes or no?
No.
Correct. It is not. Why not? Because if n is less than 1, the log of n is what? Negative. Are you with me? Remember from that graph of the log function. So this is eliminating a positive value. Eliminating positive value. But in order for that to be true, n has to be greater than or equal to 1. Is everybody clear?
Why does 0 not work?
Oh, 0 doesn't work because the log of 0 is negative infinite.
0 times whatever that is.
No, because this is undefined. The 0 times negative infinity.
Okay.
See, like if it were a half, this whole thing would be negative. See, are you with me? Okay. Now, how about this one? How about this one? How about 2n squared plus n log n? 2n squared plus n log n. And we want this to be less than or equal to, 2n squared plus n times n. 2n squared plus n times n. So what are we doing? What's the justification here?
Replace log n with n, provided that log n is
Log n has to be what?
less than or equal to n. Or greater than n. Yeah, log n has to be greater than n.
Replacing log n with something that's what?
Greater than n.
That's greater than. So when is n greater than log n?
For all of them.
Is it greater than 1 or is it 0? Is it always or what? This one is always. Do you remember that graph? This one is always. Okay, so increasing a positive value. No restriction on n. Increasing a positive value. And there's no restriction on n here. Now how about this one? This was an interesting one. I actually, somebody did this, 4n squared plus n log n minus n. And we want this to be, we're claiming that this is less than or equal to 4n squared plus n log n minus n log n. No, the log of n has to be what?
Less than 1.
No. It has to be greater. So when is the log n greater than, when is the log n greater than
It has to be
1?
greater than or equal to e. The base.
Which is what?
2.
2.
Oh, right, it's not ln of n. It's lg.
Yeah. Is everybody clear?
And that would make, wait.
So this is increasing a negative, magnitude, right? But the log n, if you increase a negative magnitude, this log n has to be greater than or equal to 2. Sorry, n has to be greater than, log n has to be greater than or equal to 1, which means what?
N has to be greater.
N has to be greater than or equal to 2. I'm making this one, oh yeah, sorry. You are right. This is greater than or equal to. Yeah, this is greater than or equal to this, provided by increasing a negative magnitude because of this, right?
So there's multiple right answers.
Oh yes,
C and N.
because that is exactly right. There is more than one way to do it, and if you get a different C, you'll get a different N not.
Yeah.
Now let's do some practice on statement execution counts. Now watch this. I have a little four-stepper. 1, 2, 3, 4. Here's statement S1. Here's 4 int I gets 3, I less than n, I plus plus. And then indented, within that body we have a 4 int j gets 1, j less than or equal to I, j plus plus, and here's just some statement S4. And we can assume that n is greater than 3. And here's our table. And I think getting this table written up is what people had problems constructing. So here's our statements: 1, 2, 3, 4. And let's start off with n equals 4. Now when n equals 4, how many times does statement 1 execute? Good. And this is saying, if n equals 4, this is saying 4 int I gets 3, I less than 4. Right? So do you see that this does its loop once when I is 3, and then it does what? It does the test, and then it breaks out. So this one will be what? This will be 2. Are you with me? Now, the first time this goes through the loop, I is 3, right? When this executes its body for I being 3. When I is 3, what is this loop? This is for j gets 1, j less than or equal to what? 3. So it executes for 1, 2, and 3, but then the test makes it 4. And this one executes what? 3. Because that's... Now, does everybody see how that worked? Now, look, what happens if n equals 5? If n equals 5, this one executes what? Once. This is saying 4 int I gets 3, I less than what? 5. So it executes what? For 3 and for 4, but then it does the extra test, so that's 3. Now is where it gets tricky. When this what did we say this outer loop executes? For I equals what? 3 and 4. So first let's do them separately. First let's do it with 3. When it's 3, this is for j gets what? 1, 2, and 3. Are you with me? 1, 2, and 3. And then what? And then the extra test, right? So that's 4, right? But that's when I was 3. Now when I is 4, the next time this goes through, I is going to be 4. So this is going to be 4 int j gets 1, j less than or equal to 4. So it'll execute 1, 2, 3, 4, and then what? And then the test. So 4 first time, 5 the next time. And now how about this one? This will be 3 plus 4, because it doesn't have that extra test. Now let's do n equals 6. 1, 4, 4 plus 5 plus 6. Are you with me? 4 plus 5 plus 6. And this one is what? 3 plus 4 plus 5. And now let's do it for n in general. Now we generalize. Now what is this one? 1. What is this one? If 4 it was 2, 5 it's 3, 6 it's 4, n minus 2. Is everybody clear? And what is this one? This one is 4 plus 5 plus 6 plus ... plus, and what's the last one? Is it n?
Yeah.
Oh, I guess I didn't need the paren then, huh?
N minus 4.
No, hold on. That's just n. Now, what is this one?
3 plus 4.
3 plus 4 plus what? 3 plus 4 plus 5 plus ... plus what? N minus 1 is the last term. Now we have to be able to do this, these summations. For number 3, what do we use? We use the fact that we know, now you have to know this. 1 plus 2 plus 3 plus ... plus n equals what? N times what? No, I think it's plus.
N plus.
I think it's 1, the sum of the first is n times n plus 1 over 2, right? Isn't it?
Yeah.
Somebody give me a confirmation there. Okay, good. So what is, so now here's my question. What is 4 plus 5 plus ... plus n, which is what we need to calculate? Well, it's all of this. It's n times n plus 1 over 2 minus what? 1 plus 2 plus 3, right? Are you with me? And if you work this out, this is quadratic. It's 1/2 n squared minus 1/2 n minus 6. Does everybody see how to do that? Because look, it's this without the 1 and the 2 and the 3.
How come it's minus 1/2 n?
Oh, sorry.
Yeah.
Oh, Yeah.
And so.
Yeah, sorry, my mistake. Plus. All right, now let me just do this next one real quick because it's time to go. So now what is what is 1 plus, now what is this? What is 1 plus 2 plus 3 plus ... plus n minus 1? What is that? That's n minus 1 times n over 2. So what did we have to calculate? 3 plus 4? 3 plus 4 plus ... plus what? N minus 1 is what? It's this. It's n minus 1 times n over 2 minus what? 1 plus 2. And if you work that out, that is 1/2 n squared. Oh, there's my minus. That's 1/2 n squared minus 1/2 n minus 3.